Good morning, everyone. Thank you for joining Mega Asia webinar. I'm Grace from Mega Hong Kong. Today, our topic is Introduction to Motor Testing, presented by Mr. Paul Locke, who is the Renewables, Energy, Rotating Machines, and Industrial Segment Manager of Mega APAC. Please note that in the webinar, you're automatically muted to prevent any background noises. During the webinar, if you have any questions, please type in the question box, which you can see on the left of your screen. We'll answer your questions at the Q&A session. At the end of the webinar, please have a fill in the survey, which you can see on the right-hand side. We'll be sending the presentation materials to those committed the survey. Attendees will be able to download an attendance certificate after they have finished the webinar and completed the survey. And the recording of this webinar will be sent to you in 2 days' time by email. So without further delay, let's start now. Thank you for joining us today. Paul, I will pass the time to you now. Thank you.
Thank you, Grace. Hello, everybody. My name's Paul Nock. I'm the Rotating Machines Manager for Asia Pacific for Mega Baker Instruments. Just a little bit about today's webinar. The introduction to motor testing will be a presentation that will be overviewed by Drew Norman, our applications engineer based in Colorado. Just to give you a little bit of background about myself, I'm the regional manager, as I said, for APAC. I also have a long history of working with electric motors in my career, joining Baker Instruments about 10 years ago now. And when Mega purchased Baker Instruments 5 years ago, I transferred across with them. I've always lived in Australia over the last 20 years, so having that, being fairly local to Asia gave me the opportunity to support this region. So the webinar itself will be on general motor testing, but the instruments involved, just to give you an overview of Baker Instruments, are specifically designed to test electric motors. They're not general test equipment that's used to test electric motors as well as many other applications. This enables the instruments to be very accurate and tuned in to the parameters that we find with electric motors. So you can see from my background there, you know, my whole working life has been involved with motors from a practical perspective. I've condition monitored motors. I've been involved with installations, rewinds, many different areas where it comes to electric motors, even vibration analysis. So I've been fortunate enough to pick up a lot of knowledge. So when it comes to questions and answers, please don't hold back and let any questions come through. There is no silly questions. So please ask away, and I'll do my best to answer in the answers at the end of the webinar. Just a little bit about the region. This is our regional kind of structure that we have. I'm obviously the segment manager, as I've just said. Michael Evangelista, he's our regional apps engineer. We have other apps engineers as well that reports to Michael. Grace is our marketing and manager based in Hong Kong. If you need to contact us, when you get a copy of the presentation, you'll probably see these emails. Please feel free to contact us. And with that, I think we'll get on with the webinar. Grace, can you kick off the webinar now, please?
Yes, I will do that now. Thank you.
Well, welcome everyone. As Meredith mentioned, today's webinar presentation is an introduction to motor testing in general. This is the first of many webinars that we'll be conducting over the next few weeks. We actually have one scheduled each week into the end of May. So definitely would recommend, if you liked what you hear today, that you go back and sign up for more webinars in the weeks to come. So let's just jump right into the material. We're going to start off by talking about why motors fail, probability of your motor failure. As many of you may be aware, obviously motors fail all the time. The probability of failure is defined by this curve here. And so at the beginning of life, we call this period of time the infant mortality period. the beginning of a motor's life, it's more likely to fail. And this is due to manufacturing defects, installation problems, maybe misapplications, a lot of different reasons. But if we get all that stuff sorted out, the motor goes on its way, it starts doing its job, then the probability of failure falls off. And then over the course of its life, it's a relatively low failure. And then as the installation ages and undergoes deterioration based on the environment that it has to live in, that probability of failure will start to creep up. And then once that installation reaches the end of life, of course, that probability of failure will increase as we see here. And so when it comes to motor testing, that's a tool that we can apply to kind of gauge, where our actual condition is and kind of identify where these higher probability failure conditions might exist. So that's what we're going to cover today. We're going to talk about extending your knowledge about motor testing beyond the use of just a handheld low voltage Megger test for insulation resistance evaluation, and beyond low voltage resistance or inductance evaluation into a broader spectrum of testing. Okay, so as you're probably all aware, when we're talking about motor testing, we're not just concerned about the motor. We're concerned about, of course, we're concerned about the motor and the insulation of the motor, bearing health, proper cooling, all that stuff. But we also need to be concerned about the quality of power that we're feeding the motor, how we're loading it, that the motor's properly applied for the job that it's being required to perform. So it's always important to keep a broad, objective view of the entire system that we're evaluating. Even the cables there in the back provide are an integral part of this whole system that we need to be evaluating. Here's a nice little pie chart. Not the best resolution, but from General Electric that kind of shows us the probability or the different, percentage of different types of failures of motors. And they break it into two pie charts. The one on the left here for motors up to 4,000 volts, you can see that the majority of failures are bearing related. And this is why, from a reliability standpoint, typically we start with a vibration analysis program, right? That's the lowest hanging fruit there that we can try to get our heads around and understand what may be causing those types of failures. And the second single leading cause of failure, and really what we're going to be focusing on today, is those that are stator related. So here we see 25% of motor failures stator related for these lower voltage motors. And then for motors that are over 4,000 volts, we see that stator related piece of the pie jump to 66%, primarily because we move away from rolling element bearings into sleeve bearings. So that becomes a smaller percentage of bearing failure because it's easier to kind of roll those bearings in and out in the field more likely. And then also for voltages greater than 6,000 volts, we also introduce an increased failure mode in the form of partial discharge and corona activity for higher voltage motors. So again, today's focus is going to be primarily on those stator-related failures and some rotor-related failures as well. All right, so let's talk about some installation failure modes. So if we're going to be testing motors, we need to understand how they fail internally with respect to the electrical failures. And again, this pie chart reiterates what we just saw, but specifically the electrical failures can be broken down into different types of failures. Turn-to-turn installation failures, which I'll describe here in just a second. Ground installation failures, which we're probably most familiar with. This is what the Megger test is looking for with respect to the insulation barrier between the conductors of our motor and the frame or the ground wall, if you will. And then rotor-related failures, especially if there's wound rotors involved in the installation systems of the wound rotors. And of course, we could also have broken rotor bars and things like that for squirrel cage type rotor designs. But you can see this, I just want to reiterate that that's a large percentage of failures we're talking about here. In the electrical realm, of the 30% of motors that fail electrically, 80% of that 30% or 67% begin as turn-to-turn failure. They may later progress into a ground fault, but their root cause was that turn-to-turn. And so we talk about turn-to-turn, turn-to-ground. I just want to briefly kind of show that what specifically we're talking about there. And here's a picture of a we call random wound stator. I think this one's out of a washing machine that you might find in your home. Now, if you could just imagine with me that we cut the top of the stator in half and then kind of rolled it out flat like a pizza dough, and then we'd have the slots of the stator laid out horizontally. That's what this image behind here is kind of representing. Each one of those groupings of blue circles represent the slots in that stator, and the blue circles themselves are the individual conductors. And so with that in mind, if we talk about the turn to ground failure, we're talking about that insulation barrier breakdown in the slot there between the conductor, through the enamel coating of that conductor, through the insulation layer that's in the slot cell insulation, and then finally to the iron there. So that's what your Megger test is going to find. If you do any kind of step voltage testing or high pot testing, that's the insulation barrier that's being evaluated. But again, that 67% of electrical failures will begin as this type of failure, this turn-to-turn insulation failure. And we have three types of turn-to-turn failures. This one that we're showing first is within a coil group itself. And this would be the smallest change in inductance that we would see. But what will happen is that these two will short together. This will induce a large circulating current flow, which will in turn produce a lot of heat, and then eventually it will break down the insulation in that area, whether and eventually it'll either burn through a phase barrier or it'll fail to ground, as we see here. But it will have begun as this turn-to-turn insulation failure. If the two turns are in the same group, in the same coil, that we just call that a turn-to-turn failure. If it's between coils, we call that coil-to-coil. This would be a larger inductive change in the circuit characteristic. And if those two coils happen to be in different phases, where it actually burns through the phase barrier, then we call that a phase-to-phase fault. And that's usually the largest energy release that we would see in a motor failure. Okay. All right, so again, understanding insulation failure, we have to understand, the prime motivation for insulation failure, and that's going to be the insulation breaking down. And so the insulation starts at a very high value. This is by design, right? So we have a motor nameplate rating, say a 460 volt motor, for example, and that rating is related to the operating voltage that we'd apply to that motor. But there's also an insulation rating. There's an insulation voltage rating. And when I design a winding, I want to make sure that there's enough insulation breakdown voltage overhead, so that over time, as that insulation deteriorates or decays away, as we see in this graph here, over time that's going to happen, I have room for that to occur so that I get a long life out of my motor. So of course the curve is shaped in that way because over time the environment's going to act on that insulation, and primarily the main driver for that deterioration is going to be heat. Heat can come in a variety of forms. We'll talk about some of the things that drive insulation to degrade over time here in a second. But what ends up happening then, of course, is as the insulation breakdown voltage goes down, eventually it's going to arrive at bus voltage. And when the insulation can no longer withstand bus voltage, and that's where we're kind of doing our Megger testing at, right? When it falls below that level, that's where motor failure occurs, right? That's when the phones start ringing and we start going to the warehouse looking for replacement motors. All chaos ensues. So we'd like to be able to tell earlier where we are in this curve so that we don't have to react. We can be proactive about our maintenance decisions based on the actual condition of the insulation and not wait for it to find us, right? So that's the goal of broadening our testing, broadening our testing endeavors. So one of the things that a lot of people aren't aware of is that your motors endure a much higher voltage stress in its day-to-day operation. Just by the normal switching, the motor is exposed to voltage levels as high as 4 times nameplate voltage. So again, for that same 460 volt motor, it has a design insulation breakdown voltage of say 28,000 volts to ground, but it has to always be able to endure voltages as high as 2,000 volts. Otherwise, it'll start to degrade it at a much more rapid rate, and then eventually, of course, it will fail, which is what we're trying to avoid, unexpected failure. Okay, yeah, and so when the insulation drops below that switching voltage surge level, then we got internal arcing, and that's what the motive stress that's going to cause that insulation to degrade more rapidly at the end of its life. So another thing to keep in mind about, of course, the rate at which this motor's insulation is going to degrade is going to be based on its environment. So here we have a motor A, and of course, when that insulation drops, as we said, drops below bus voltage, that's where the failure is going to occur. But we might also have motor B, and motor B is the sister motor of motor A, if you will. It's exactly the same design, but for some reason it's living half the life. And trying to understand why this motor's failing more rapidly, more frequently, is kind of one of the goals as well of motor testing, to identify the different factors that could lead to that accelerated degradation. So those factors are kind of defined, primarily by the environment, and the main driver, as I mentioned earlier, is heat. So let's talk about those factors. What are the factors that lead to insulation failure? So I mentioned heat, and we know that that thermal aging is the primary driver for insulation failure. And there's a rule of thumb that we say for every 10 degrees C increase in the temperature of the insulation, the rate of insulation degradation will double. So it's going to deteriorate at a much faster rate the hotter that we operate that motor. So if cooling fans break, or we overload the motor, certain things like this, that's going to lead to more heat in the motor. If we cover it in pulp at a paper mill, right, that's going to insulate and keep that heat in, and that's going to degrade the insulation at a much faster rate. And again, 10 degrees C it's not a whole lot of increase in temperature, but we're going to have this really huge impact. Just coming back here really quick, right? A 10 degrees C increase in the stator winding temperature moves us from a motor A to a motor B situation. We lose half the life because it's degrading at twice the rate. So that's, thermal impact is huge. Okay. And contamination, this is something a lot of us struggle with. Unless you're at a nuclear power plant or a really clean pharmaceutical plant, you're probably contending with contamination in some area of your plant. And contamination is so versatile in how it attacks insulation, right? It can act chemically, certain caustics or acids can get on that insulation system, even some additives in grease. We greased our bearings, and we've got that one guy that's really gung-ho about his job and greasing those bearings, and he greases it so much it gets into the windings, and then the windings will degrade at a more rapid rate. Or maybe it's just the normal environment that the motor has to live in. It creeps into the motor and actively attacks the insulation system. Contamination can build up on the windings, leading to that thermal insulation. I mentioned pulp as an example of that earlier. Abrasive wear, those of you that are in the cement industry or coal crushing, right? That really abrasive material gets in the airstream and causes the insulation to degrade physically, right? So it literally sandblast, if you will, away the insulation till in some cases bare copper is exposed, and of course you're going to have a ground path at that point. And just another thing that we have to deal with a lot of places is moisture or the presence of water. I deal with a lot of customers that have submersible pumps, and that's always a big concern. Or if you have underwater cable trays, right, an old plant that water seeped into the cable tray system, that moisture can really wreak havoc. If you're in a paper mill and you have the wet end of the paper mill, right, moisture is a big headache for a lot of us. And so being able to understand and evaluate moisture would be really important as well. So insulation can also degrade mechanically, just the movement of the windings. In our next webinar, I believe that there's maybe a video we can show you that physically demonstrates this significant amount of movement of the winding. And then also the windings grow thermally as we heat them up, especially during the starting cycle where we have a high inrush current. That high inrush current, of course, is going to yield as a squared function of current, I squared R, will yield a high thermal impact on that winding, and it'll grow thermally in the slots. The winding will elongate in the slots, and that elongation or growth in the material of the coil or in the movement of the coil during the high torque feedback on the coil will cause that insulation to wear out over time. So there is a mechanical element there as well. And then I mentioned earlier in the presentation, the voltage spikes up to 4 times bus voltage are constantly impinging, impacting that insulation in such a way as to, cause it to degrade over time. So VFDs, they switch at a rapid rate, so we're getting that even higher stress from those applications that are on variable frequency drives. All right, what's some other factors? Let's see, power quality, and this is a big group of stuff here. Power quality we have to talk about. If we have overvoltage, right, that's going to lead to a saturation of the iron, and that heat that's formed in the core iron of the stator will cause the insulation to degrade. Undervoltage, of course, leads to higher current for the same amount of delivered power. If I apply a lower voltage, it's going to have a higher current to meet that power demand, and that higher current, as a squared function of current again, will produce heat. In a three-phase system, we can have an imbalanced voltage, which will lead again to imbalanced currents, which is of course not desirable. I'm going to have to push more current into the motor to do the same amount of work, and that just again adds up to more heat. Distortion, if I have a lot of VFDs in the system, that could lead to distortion on my bus that I later feed to motors that aren't even on a VFD. That could lead to extra current and of course extra heat. The distortion can come in the form of harmonics and non-harmonics. So it is important to understand the characteristics or the specific nature of that distortion, especially when we're trying to troubleshoot or identify the particular source of that distortion so that we can remedy the situation. And of course, corona and partial discharge is another thing that we need to be aware of when it comes to damage in our installations. Probably not in the power quality, although voltage level does contribute to the presence of partial discharge. It really comes down to, it should be its own bullet under power quality. Comes down to the design of the motor. If there's voids in the insulation, for example, that can lead to internal partial discharge, which will cause basically acids to form internally and then eventually lead to turn-to-turn or turn-to-ground internal failures. So being able to detect the activity, partial discharge activity, is also another important element of a motor testing program. All right, but wait, there's more factors, right? We'd be amiss if we didn't talk about load and operations, right? Because oftentimes in a plant, we're trying to get the absolute most we can out of our motors, and overloading, of course, is one of the main contributors in a lot of cases to extra heat. And again, every 10 degrees C, what is that going to do to our insulation? It's going to double the rate of degradation. Maybe we got the wrong motor for the job. I know early in my experience in the paper mill, we found many cases where there were motors with the wrong NEMA design. You put a motor in there with a NEMA B design where it needed a C or a D, and now we're taking forever to start that motor up. It does actually do the job, but it's not doing it efficiently. You got these long startup times where that inrush current is being sustained for longer periods of time. That's going to drive my insulation to degrade more rapidly, and specifically in those periods, those longer startup periods. So that's another one to keep in mind. You may not think about. It's not the most obvious one. Frequent starts and stops. This is, how do you clear a paper jam? You just hit that jog button, right, until the system starts running again. And that's definitely not the right answer. There are limitations. ESA has a nice a book that they hand out that includes a table that tells you how often you can start a motor, how much time you should wait between starts, and quite oftentimes we're either overriding protections or there's not protections in place to kind of limit that, and operations might exceed the start-stop recommendations, and of course wear out the insulation prematurely. And so during starts and during shutdowns, that's where we experience the high voltage spikes I mentioned earlier. Of course, frequent starts also have a high, almost up to 300% of the rated torque. So we're likely to damage our rotors if they're across the line starts, especially. And overheats, of course. Voltage spikes, I mentioned. Inrush currents as high as 10. I think the highest I've seen is 13 times the full load rated amps for that short period of time. But again, it's a lot of current that leads to heat. I mentioned the coil movement due to the counter torque. As that rotor's producing torque is pushing back on the stator, that causes the coil windings to move. And again, next week we'll show you a video of that coil movement. It's really impressive to see. Other things to keep in mind: latent manufacturing faults. So just things that are waiting for you, right? You buy a motor. If you don't test that insulation, you're making an assumption that you're being delivered a quality product. And maybe it was quality when it left the factory, but it sat on that truck. The truck got blown off the road due to a hurricane. You never know what's going on with that motor until you get it. So, being able to evaluate it and put your quality stamp on it on your end, it's probably ideal before you sit it in a warehouse where it's going to sit there and wait for that most critical time when you need that motor, and you don't want to find out at that point that you had some kind of manufacturing fault. And here's just a list of kind of some of the things to look out for there on the manufacturing side. All right, so now condition-based assessment. So how do we use electrical testing to kind of understand where we are? So again, this is a more of a general brief overview. In the next few weeks, as we drill into static specifically and dynamic testing specifically, we'll get into the details, but I'm going to give you an overview of kind of how all this kind of fits together. Of course, here's a nice analogy. We've got a puzzle piece. This is our equipment. This is our systems that we're concerned about. And here's this missing puzzle piece. This missing puzzle piece represents the problem that we either know about or maybe we don't even know about it. And so we apply different technologies, right? We want to enhance our senses so that we have the ability to understand the condition of our equipment beyond just putting our hand on it or hearing it or relying on protection systems to tell us there's a problem. And so maybe we apply the vibration, right? Because the vibration is going to cover 50 to 60% of our problems with our motor. And that covers all these puzzle pieces on the right. But our motor problem, as you can see here, is only barely covered vibration. Maybe there's a little uptick in the 2 times line frequency, for example, in the spectrum. That might indicate an electrical problem, but we really don't know what that electrical problem is. And so the vibration guys call us in the electric shop and say, hey, you got a problem with that motor, you might want to check it out. Oil analysis, there's some nice overlaps here. But electrical testing for this particular problem is really what we need to apply to understand that problem. And electrical testing comes in two forms: static testing, and specifically static testing is looking at the motor while it's offline, de-energized, locked out, tagged out, hopefully. We verify that de-energized, and then we can go in and evaluate the circuit condition, evaluate the insulation condition, kind of understand where we are on that breakdown curve. Dynamic testing tells us about the environment that the motor lives in. So that's we need to be mindful, though, because it might be vibration, it might be thermography, there might be other types of technologies out there that can identify the problem at first. But static testing and dynamic electrical testing are going to help us specifically identify the issues that we're having with that particular motor. So motors, as I mentioned earlier, they begin as turn-to-turn faults, right? 67% we had in that one pie chart. The turn insulation is the weakest in the motor. As we saw on the breakdown curve, that was around 8,000 volt level versus the 25,000 volts to ground. As chemicals act on the insulation, it's going to break down that turn-to-turn insulation. We'll show you this video from the GE study from Crawford that shows you that movement that causes that turn-to-turn insulation to wear out over time. Of course, damage caused by, I hate to point to the winder is the problem, but the winding process, or that could be anything from the the wire manufacturing enamel coating process all the way to the forklift driver that's handling the stator after the winding process. Who knows, during assembly or whatever. VFD spikes cause heating. So all that stuff leads to turn failures first. And of course, in static testing, we have a means of actually looking at that turn insulation. So that's that's going to be a really big help for us when we're trying to identify these early failures. So static testing, again, is measuring and tracking electrical properties of the winding circuit in an effort to determine its health and reliability while the motor is de-energized. Again, this is an offline test, verified, dead. We do that by kind of breakdown voltage testing in a couple different ways. We have low voltage testing. This includes like our resistance, inductance, capacitance measurements, Megger testing, where we're measuring specific electrical parameters at or below nameplate voltages to determine a change in the electrical circuit properties. So that's kind of looking at trending, comparison over time, or relative to known values, and we look for percent deviation from those known or standard values. And then we have high voltage testing, and high voltage testing is where we're evaluating now that insulation's ability to withstand those high voltage surges that it's seeing over its life. So testing motor insulation at voltage levels similar to those the motor encounters in its normal environment to determine the integrity and reliability of the insulation system. And that helps us to define the insulation condition with respect to end of life, right? So as we approach the twilight years of that motor, if you will, we can make those end of life decisions that will minimize the impact of a failure on our operations, which is where the real money is, right? Making product is what we want to always be doing. And if we can schedule an outage, schedule a motor change out, and not have the motor define our schedule, then we can be proactive and do good things for our companies. Okay, so that's static testing. Now, dynamic testing, what is it? The ability to find power condition, motor, and load-related issues. So remember that system diagram at the beginning with the power supply, the motor, and the load? This is what dynamic monitoring is looking at. I almost would want to take that word motor and just rip it right out of there. It's dynamic electrical monitoring because we're looking at the entire system. And what's cool about our product in the EXP 4000 is it does a really good job with power quality. It tells us specific information about the motor and its response to the power quality. And also we have a set of information that's load centric. It's defining what the load is demanding of the motor. And so we get a nice tool that we put right in the middle of there that measures the voltage and currents, right? But then we work this algorithmic magic to define what the torque is doing, what the load's demanding of the motor, and how the motor's rotor is responding and the ability to produce torque. So if we have broken rotor bars, if we have a broken vane in the pump, we can a broken degraded bearing, we can identify kind of all that stuff with the online dynamic monitoring. So that's going to help us understand the whys, right? The root cause analysis. Why is my motor failing? Not only am I at end of life, but how did I get here? And so that we can proactively go out and make our plants better so that our motors then can live in an environment that's more suited for a longer life. So I like to say that when starting a program, I want to buy a static tester so I can identify motors before they fail, but then I want to buy a dynamic tester so that I can identify those areas that are causing my motors to fail. So yeah, all that stuff there, power quality, motor, and load-related issues, helps us define mechanical issues. You can see some examples there. Again, in the coming weeks, we'll drill into these specific tests and how all that works. You see some power quality issues there. All that stuff is basically mirroring what we talked about earlier in the failure modes of insulation even. And then again, a great way to think about this is defining the motor's operating environment. Okay, back to this curve. All right, so just another way of thinking about this, right? So the insulation is breaking down over time. It's the breakdown voltage is going down over time. Eventually it's going to fail. So if I can institute static testing, it's basically going to give me a dot on that curve. Where am I at on that curve today? If my test is great, everything's passing, and I got a nice little green result, that's awesome. But eventually I'm going to get some results that I can interpret as not failing, but I'm starting to deviate from a solid good condition. And again, next week, Leslie Reed, our application engineer / training specialist, is going to go over some of those specifics with you guys. to how to identify those caution areas on the curve as we approach the end of life and the failure of the motor. So, ideally, we don't want to wait till we're here. We want to identify our stuff prior to, and the static technology is definitely going to provide that early warning system. So dynamic testing kind of helps me understand which curve. Am I on a motor A curve or am I on a motor B curve? And all those different dynamic parameters that we evaluate and load conditions and application scenarios, dynamic testing will help us identify whether we should be more concerned when I get to a caution state and I'm in a motor B situation where I know I have a poor power quality situation because that drive we purchased last month didn't have proper load filtering, but we went with it anyway. And, of course, next outage, we're going to get a filtering system, but my insulation is degrading more rapidly. I need to respond to that differently than a motor A situation, and that motor that's running at 80% load that only starts one time a year and, is in a nice, clean environment. So again, dynamic testing helps me understand severity of my environment so that I can respond to that condition as well. So some examples, this is a screenshot of the EXP4000, what we call the surveyor software. And you can see we're looking at a VFD motor here. All the different buttons are kind of laid out so you can drill into your area of interest. I want to look at power quality parameters associated with voltage. I click on power quality. If I want to look at torque related issues, I click on torque. So spectrum include rotor bar spectrum, voltage current, torque spectrum. Here you can see that a little bit of that torque waveform, that mechanical indication that we have there. And then up here at the top, we have our voltage waves and our current waves. And of course, for a VFD, that's pretty common. We get this really high frequency content, PWM driven shape of the voltage that's going to be applied at a specific voltage and frequency. So the parameters of dynamic testing is looking at voltage, of course, voltage, current, load. Each of these parameters could be high, low, imbalanced, distorted. There might be specific peaks of interest in the current, like a rotor sideband current, for example, that might identify a specific problem associated with broken rotor bars. And here you can see some of the results and causes. And again, I'll stress that in the next few weeks, we'll get into these with a lot more detail, but I'm just giving you a good look at them here to start. Of course, high loading, we mentioned, overloading causes increased thermomechanical stress, and the dynamic system is going to tell us exactly where we are with respect to loading. And it's not the only thing, loading's not the only thing that creates the heat, right? If I have an under voltage condition, an imbalance condition, high distortion, I could have all three of those things, and I could be overloading the motor as well. So really kind of quantifying each of those, where the low-hanging fruit is for getting those things remedied, really gets defined when we look at dynamic data. Here we can see specifically look at torque, oscillations in torque, which could show us mechanical defects or maybe even process-related issues with the load system itself. Maybe it's cavitating because of a low suction pressure. That there's a really distinct, we will show you that in a couple of weeks, a really distinct signature in torque when you have a cavitation issue in a pump. It's pretty cool. High spectrum peaks associated with specific frequencies of interest can also be seen in the torque spectrum. And it's just like vibration. There's a nice correlation between the two there. Startup analysis, looking at a motor during that starting cycle, right? We talked about how aggressive that is on the motor insulation system, right? The high inrush current, the high I squared R loss from that 10 times current flow, that up to 300% torque, causing the windings to wiggle around and abrade away. And of course, voltage during a startup dips, and that voltage dipping can lead to longer startup times, basically is what we're worried about there. Longer startup times mean a longer period where we're sustaining that high inrush current, which is definitely not the best idea. That high inrush current is producing all that heat. Okay, now we'll look at some of the, next week we'll be drilling into static, and of course the AWA, there's just some screenshots of the different little pieces of data parameters that we have in the AWA desktop software, where we look at each of the individual parameters of resistance, insulation resistance with respect to PIs and megers. This is the low voltage resistance testing here. Step voltage testing, where we're increasing the voltage and looking for deviations from a linear response. We see this nonlinear response here. And then of course in the surge waves as well, looking at the stability of the surge waves. And if you don't know what surge testing is, again, I recommend you come back next week. We're gonna show you some of that, and then later on in May, I believe we have another section where we're going to be talking about a specific parameter that we use to evaluate surge called pulse-to-pulse error area ratio. So that's coming up. Here's the parameters. So resistance, inductance, capacitance. These are, again, low voltage tests that allow us to evaluate the insulation in the circuit, not the insulation, sorry, the circuit characteristics, part of which capacitance and inductance for some extent is defined by the insulation. But again, those are low voltage tests where we're not really stressing the winding anyway. We're just getting a quantity that we can trend and look at or compare to known values, looking primarily for imbalance in a lot of those situations. Of course, insulation resistance, low voltage testing, where we're looking for low mega readings that might be indicative of some kind of degraded insulation, but more likely the presence of contamination and moisture in a lot more cases. And that could be also include not only the motor, but also the cables. Always important to keep that in mind. A lot of this testing can be performed from the switchgear. Majority of this testing actually can be performed from the switchgear. There are some rare exceptions. Of course, PD testing has to be done at the motor, but low voltage resistance, insulation resistance, step voltage, and surge testing can all be accomplished from the switchgear. So that's good, right? So we don't have to disconnect a bunch of stuff to get to what we need to get to. So insulation resistance, the next level is, of course, step voltage and looking for that nonlinear response. Again, Leslie will cover this in a lot more detail. Surge testing, we're basically impulsing on the winding some energy, and we're looking at how that winding is responding to that energy. This kind of a ringing, it's almost like a resonance test, if you will, like a ring in a bell. We're kind of looking at, are there any cracks in our bell? In this case, are there insulation weaknesses that the surge test can identify? And that's specifically looking at the turn-to-turn insulation that we talked about at the beginning of the presentation. So we evaluate that for the wave stability. We evaluate the balance of the waveforms in some cases, specifically when the rotor is removed. And then we can also use the surge test to evaluate partial discharge. So we have a tester, the DX tester, for example, that will look at the surge wave and identify high frequency content that's associated with partial discharge. All right, so let's take a look at, real quickly, we'll look at a couple of cases, one for static, one for dynamic, and then we'll wrap up. And if you guys have any questions for me, we can get some of those done with the time that we have left. So this particular case, we have a 4160 volt motor, 1500 horsepower. This one's here in the United States, and I believe this was in southern Louisiana at our Strategic Petroleum Reserve, actually, here in the United States. So we actually tested two motors. They were exactly the same nameplate, just different serial numbers. Instead of a 1, there would have been a 2 on the second motor. And in this case, it was the first time we were testing. So we didn't have any trendable comparisons, no time trends. But we were able, because they're exactly the same design, to make a comparison of what I call comparison of like design. So we're trending by comparison in this case, and looking for deviations. And so you can see there's a, here's a spoiler alert. We got something that's red, but it's not resistance. There's a slight difference in resistance here, but it's not significant. Of course, we're entering temperature so we can compensate for these values and then later compensate for the insulation resistance values that we measure during Megger testing. Here we start to see some deviation, right? Still passing a Megger test. We have 1100 megohm or 1.1 gigaohm corrected on this motor. We have 226 megohms on this motor. Now, either one of these readings might be acceptable for that environment, but they're definitely looking at a 5 times deviation there when we do this comparison of like design. So there's information already that there may be some issues with this motor too. Here are the PIs, and here's our second glimpse at something that maybe not exactly ideal about the situation, right? Motor 1, we have a nice low current. We already kind of knew that from the 1 minute evaluation, but we continued that evaluation for up to 10 minutes to identify how the insulation is polarizing over time. And in motor 2, what we see, this little dip down is a scale change. We don't necessarily need to worry about these little dips. But what we're concerned about here in motor 2 is that we see this asymptotic decay all of a sudden just kind of level out and flatten. And something is holding that current level up at around the 5 microamp range, where this one was continuing to decay as low as 0.5 microamps. Here we don't see that. And now this is a clear indication that we have a secondary parallel path out there somewhere in the circuit. And so we identify this as a potential contamination related issue. Again, it's still passing, I believe. Actually, this was, let's see what that PI value, I believe it was like 1.9, so just below the threshold of 2.0, which isn't unusual for a field measurement, but again, giving us a clear indication that there may be something amiss here that we need to drill into and identify. Then we move on. Like, so if we just left it here, we would have some questions, but you know, it's 200 megohm, that's still good. We probably don't need to be worried too much. But we move on and we do the step voltage test. Now remember, step voltage testing is increasing the voltage so that we can evaluate the insulation's condition to withstand those high surges that it's going to endure during the switching cycles. And so we want to see this, like in motor 1, we want to see this nice linear response. And motor 2, we see this deviation from linearity. It starts out linear, and as we approach the higher test voltage, the recommended test voltage, in this case from IEEE 95, we see this nonlinear response. And then we also see the characteristic of the current, where it's nice and smooth asymptotic decay. On the last step, we start to see an erratic nature in that current. And so this test in the AWA data is listed as a pass, but we have some qualitative and quantitative, actually, indications that there's instability in that insulation. If I'm not going to do it, but if I were to go one more step above, if I add another 1,000 volts, I can interpolate that this motor insulation is probably not going to be able to withstand that, and I know exactly where I am on that degradation curve. We also did surge testing, and surge testing revealed no issues. So the turn-to-turn insulation is sound, but we have this problem with the ground. And so based on those indications, we pull the motor out of service, we send it to the motor shop for evaluation, and what we find is, upon investigation, the motor with the nonlinear indication had a high amount of internal contamination caused by the accumulation of dust and oil. The oil was present on the windings due to a leaky seal. So the seal clearances had opened up. There was an internal fan that caused a negative pressure, and that actually caused a draft across the sleeve bearings, pulled oil into the winding, where oil and dust and stuff started to accumulate on the connection end, and that ultimately led to those surface leakage paths that we saw in the PI, and then ultimately the departure from linearity that we saw in the step voltage test. So the motor was repaired, returned to the warehouse. They didn't have any downtime caused by that condition. They found it early. What a great story for those guys. Okay, last case is a dynamic case. Here we have a coal-fired plant. This is a utility, a power generation plant. Probably one of the first examples of the EXP being used in the field to identify a problem. Of course, we send this thing out there that's supposed to be an efficiency estimator, and the first thing they do is they diagnose a pump problem, right? They have three vertical pump motors connected to a common discharge header. They didn't have individual instrumentation on the discharge of each pump, just a common header information. They knew they were having flow-related issues, but they weren't really sure how to approach it or what the extent of the issues were. That dynamic data collected on the pumps revealed this. You don't have to be an expert to realize one of these things doesn't look like the others, right? Pump 3 is definitely doing a lot of different stuff than Pump 1 and Pump 2. Pump 1 and Pump 2 have a nice sustained torque level, very low peak to peak, we call it torque ripple. But Pump 3, on average, is only delivering about 60% of where it should be, and it has a really high erratic torque signature, the high torque ripple. And this is one of those indications of what cavitation looks like. So based on what they saw here, they were like, all right, let's go ahead and pull pump 3 out. They pulled pump 3 out, and this is what they found. They found that this shroud here that actually corroded, the fasteners had corroded, that shroud had fallen off the pump, and they had a large amount of internal recirculation, of course, cavitation. You can see the impingement damage on the impeller blades there. It's a bad situation. So there you go, using dynamic testing, right? Dynamic system testing to evaluate, in this case, a mechanical failure. And then they were able to get that guy repaired prior to, I guess later on in the story, one of the other pump shafts ends up shearing. And if they hadn't have repaired this, they would have been limited in their production capability. So at the end of the day, it really saved them a lot of money as well. All right, well, that gets us to the end here. And so thank you for taking the time to join us and listen to me ramble on about motor testing, which I love. If you have any questions, now would be a great time.
All right, so here comes the Q&A session. If you have any questions, you may type into the question box. Paul will answer your questions. And for those of you who are leaving, please remember to fill up the survey, which is on the right-hand side of your screen. We'll be sending the presentation materials to those fill up the survey. And don't forget to download the certificate before you close the webinar window, which is the icon on the right-hand side of the bottom control panel. So, Paul?
Yes?
Yes, we got some questions here. Maybe we can answer them now.
Okay.
All right. The first one is, what is the minimum insulation resistance allowed to do this test?
Okay, I did type an answer in, but there are basically various different types of standard organisations. The most commonly used for insulation resistance to ground is IEEE. They have what they call a standard, IEEE 43, that indicates 1 megohm for the majority of electric motors is the kind of cutoff. Any less than that, then it's not safe to start, as well as many other electrical applications. So that's kind of the rule of thumb. But certainly, if I was a manager of my motor plant and I had a reading that any less than 50, I'd be concerned. I'd be wanting to know why. That's why we should be doing predictive testing, because on a regular basis, we look at deteriorations to be able to plot the intervention at the right time. So IEEE 43 is a common one, but there are many other organisations, IEC, ESA, and various other people that recommend. We try not to get too involved with recommending any particular organisation, but it's up to the client what they follow.
All right. Thank you. And the next question is there a way to test magnetic wedges and make sure they are in good condition?
In my experience, working for a large motor service shop and working on many high voltage motors, we used to do this visually. I think there are acoustics and various other things that you can use that give a debatable response, I think. But, for me, it's usually we used to literally tap the wedges with to look for looseness and listen to the sound, because once they're all varnished together and they're solid, as you run a kind of a runner along the wedge and you tap it, if there's any hollow sound, it means there's looseness there, and that means that when the motor is up and running and starting, stopping, the inertia makes the coils actually move and they become loose, and therefore, because they're loose, the insulation wears away that much quicker. So it's a good question, but in my experience, it tends to be done by the motor experts, if you like, service companies, and it's quite difficult to spot 100% through any other method. But that's just my experience.
Okay. I guess we have already answered the other questions by test. So Anyway, if you have any further questions, please send us email to megahongkong@mega.com. You can also go to our website, mega.com/webinars, to look for our future webinars. And as a reminder, we are having another webinar on motor testing next Thursday. About the topic is ADX, the next step in motor testing, and Paul will be our presenter as well for next Thursday. The time is 10 a.m. in the morning. So please join us. Please go to the website and sign up for the webinar. All right.
Yep. The webinar is going to be based on more practical. One of the questions that I answered earlier was how practical. What tests should we do? And what we've been able to do with one of the things that Baker Instruments is very strong at is put in all the relevant tests that we feel are practical. There are lots of various tests that all show values that can give you good information, but the selection of tests that we put into one instrument for us are the key tests needed to give quick, fast indication of whether you're going to have an issue immediately or whether you've got an issue that's pending and that is predictive. So these tests are incorporated in this new instrument that we're releasing next week. So we'll be going through the different tests and explaining why we do them.
Yes. So please join us. We hope to see you again next Thursday. So I think that's the end for today. I will thank you all for attending. Thank you, Paul, for your answering questions and the presentation. And we hope to see you again next Thursday. Thank you. Bye-bye.